The transition to revolutionary science happens when significant anomalies turn up, and significant anomalies are problems which, contrary to the expectations that you have in normal science, cannot be solved. And after a while, even when the best people have tried for a long time, then people get the suspicion that it's not their own inability why they can't solve these problems, but that the framework, the guiding framework of normal science, is just unable to do so, such that they think that they have to give up this form of normal science that they practiced so far and have to find a new framework in which normal science is possible again. And that means then that we come into a new practice of science, namely one in which you cannot rely on the traditional way of doing science, but you're trying out new ways and try to invent new frameworks in order to re-establish the practice of normal science. I have described to you revolutionary science now, and the next step will be, we had discussed that a little earlier, I think 2 weeks ago, the parallels between this phase of revolutionary science and pre-normal science, because there are similarities and dissimilarities, and I want to discuss these dissimilarities and the similarities of revolutionary science and pre-normal science, because you learn something about revolutionary science in this way. Now, revolutionary science, first of all, differs from pre-normal science in that there is a consensus about the significant anomalies to be solved. That's a very important point. In the face of pre-normal science, people even disagree about the range of problems that have to be solved, because the limits, the borders of the area are just not clear, and they depend in the way how you look at it. I described to you the problems of electricity theory in pre-normal science, and people differed in what is very important to be solved and what is not so important to be solved. That is different in revolutionary science, and of course the difference is that in revolutionary science originates out of a phase of normal science that was previously in place. And therefore, for instance, in the case of Bohr's model, it is absolutely clear that the new theory that comes after Bohr's model must somehow be able, for instance, to confront the helium model, the helium atom, right? Because that is something the theory couldn't solve, and it was absolutely clear it must be solved. So everyone knew this is an important problem, and a new theory should be able to solve the helium problem, right? That is because that results from the failure of the old theory, the old phase of normal science, to solve the problem, and therefore people know it's an important problem that must be solved. So this is one of the things that we have, so to speak, a consensus about the problems that must be solved, because they are the result of the failure of the former phase of normal science. There's a consensus about the significant anomalies must be solved, and again, a difference to pre-normal science, there is a consensus and a need to preserve or reproduce the results of an earlier accepted theory, right? Again, this is different from pre-normal science, because in pre-normal science you don't have anything, from the past which is secure. And in revolutionary science, the older theory was able to produce this and this result, and therefore the new theory must also be able to produce this or that result, from the older theory. So we have a difference here, and the difference is, of course, just the difference that before pre-normal science, there is, so to speak, nothing, but before revolutionary science, there is a phase of normal science that in the end failed to solve certain problems, but was able to solve certain problems, and therefore this revolutionary science gets a sort of orientation from this failure of the earlier phase of normal science. Okay? So that's the main difference between pre-normal science and revolutionary science. On the other hand, there are also parallels or similarities between pre-normal science and revolutionary science, and exactly these similarities we discussed a week or 2 weeks ago, namely There is no general consensus. People disagree deeply about the way how to proceed with science and how to go about it and how to solve problems. There's really disagreement about it, and even these disagreements may cluster into schools. So there are competing schools trying to develop a certain approach, and the approaches differ, and there is no consensus about these approaches. So there is also this parallel to pre-normal science. So it's, I think, quite plausible that we have both these similarities and these differences, the differences arising from the fact that in revolutionary science there was previously a phase of normal science which is lacking in the phase of pre-normal science, and on the other hand the lack of a consensus that leads then to certain schools and therefore a structuring of the scientific community into schools which is similar in pre-normal science and in revolutionary science. Okay, is that somewhat plausible, right? These are the phases you probably never experience in your own life because it's very rare, these phases of revolutionary science. And if you are in well-established areas, then the paradigm theory would say you are usually in normal science. If you look at certain parts of physics, they are really in a phase of revolutionary science. If you look at the Standard Model, then people know the Standard Model won't be the last word because there are so many things that you cannot explain, and you should be able to explain them. For instance, one of these big accelerators now in Geneva, the LHC, the Large Hadron Collider, is just a machine that shall produce data such that some of these controversies can be resolved. That's the hope that's connected with it. Okay. All right. Now let us assume that we achieve during normal science the transition then to a new phase of, that we have a transition from revolutionary science to a new phase of normal science because people find a new way of practicing science, and they find a new model or a new theory, a new paradigm such that the practice of normal science becomes possible again. Then people are very happy, and this transition is then called a scientific revolution. It's really a revolution with a parallel to the political revolution because you change a guiding framework by a different one, right? That happens in a political revolution as well. It's a process that's not completely rule-guided. It's a process in which you have to improvise, and you try to establish a new order, so to speak, a political order or an order of normal science, and therefore there are some parallels. It's a little tricky to describe this parallel in more detail between political revolutions and scientific revolutions, but that must not bother us particularly. There are some parallels, but they are tricky, as I said. Now, this transition then to a new phase of normal science is called a scientific revolution, and that's a very interesting process, and it's a very delicate process that I'm going to describe now in a little more detail. This transition happens, as I already indicated, in analogy to the transition from pre-normal science to normal science, namely due to an extraordinary achievement. Right? It's the same that one of these schools of revolutionary science produces an extraordinary achievement such that people say, in the same way as in pre-normal science, that is probably the right way to follow for the future. Right? It's just an extraordinary concrete achievement, a solution of one of these outstanding anomalies. In the case of quantum mechanics, it was not the helium atom, that came a little later, only in 1927. But some of these extraordinary problems such that people believe now this will be the new guiding framework. And this is, again, this happens in analogy to the transition to pre-normal science. Now, if you compare the old phase of normal science with the new phase of normal science, then we have a very particular and tricky relationship. And that relationship is described in paradigm theory as incommensurability. It's an incommensurability between these phases of normal science, or one can also speak about the incommensurability of the new and the old guiding theory. Now, I don't know whether you are familiar with the word incommensurability. Have you ever heard that word incommensurability? No, it comes from mathematics. It's a discovery of Greek mathematics, and it means, well, let me explain that quickly. It was a very important discovery in Greek mathematics, and it led to the exclusive development in Greek mathematics of geometry and not of algebra. People in Greek mathematics developed geometry, Euclidean geometry, but they did not develop algebra. Algebra was then a development in the Arabic countries in the Middle Ages. The name algebra is an Arabic name by origin, and that was one of the big contributions of Arabic science of the Middle Ages, that they started to develop algebra, and that was then taken over by the Western tradition, then further developed in the Western tradition. But that was, of course, in the Middle Ages, very, very important achievement. Why didn't the Greeks further develop algebra themselves? Why didn't they do it? And that was the problem of incommensurability. And the problem of incommensurability is this. If you have a square, and you look at the diagonal, and then you say, okay, I express this side here, the side A, I express with certain units. The units I take U, for instance, and then I express this by a certain number of units, say in centimeters, and then I express the length of the side of a square as so and so many units. So, for instance, 5 centimeters, right? And then the question is, what is the length of the diagonal D of this square expressed in the same units, right? So you say, okay, this you express, you choose some units, right? Here are the units, and then you express it. So A is in this case 6 units, okay? And then you say, D is how many units? Right? That's a completely natural question. If this is 5 units, then you can ask, is that 7 units or 8 units? Or if you can't express it in centimeters, then you take a different unit, a smaller unit. Okay, and then you say, what's the number of units to express the diagonal? In terms of a units, you can express the side of a square, which seems to be completely natural, right? Completely no problem, right? The discovery was that that problem is impossible to solve. There is no unit. There is simply no unit. In principle, there is no unit such that you can express the length of a side of a square, that you can express the side with the same unit as you can express the diagonal. There simply is no unit. That's very strange. Well, we know the solution now, because the point is that D is square root of 2 times A, and that's an irrational number, right? That's a number that's very strange. It's not a ratio between 2 numbers. And that means incommensurability. So incommensurability or commensurability means you have a measure, the unit, the measure for A and D, right? That would be the U. But the fact is there is no unit by which you can measure both A and D. There simply is no unit, right? It's impossible. And therefore, the relationship between D and A is called incommensurable. Incommensurable. Incommensurability meaning, it's a very simple meaning straightforward from mathematics, there is no common unit. And that's just the word. Measure is, so to speak, the unit. Commeasure means together, and incommeasure means no way, right? It's the negation. So incommensurability means nothing but there is no common measure. And the unit would be the measure. If you measure it in centimeters, there is no common, so you can't express the A in terms of 5 or 6 or 7 or whatever it is, centimeters, and at the same time express the diagonal in terms of centimeters. Right? That's just not possible, right? With the N and M, and here there are natural numbers. numbers. All right? So this was the discovery in Greek mathematics, and the result was that Greek mathematics said, look, this is a perfectly wonderful straight line, right? I can draw it. So I can do geometry, right? It's no problem. This one here, a right angle here, and then I draw the line. No problems. I can deal with it in geometry. But I cannot deal with it when I use numbers. And therefore, numbers is bad mathematics, because you can't even express that. And therefore, I don't want to have numbers. So the Greek decided, and that's of course a very good argument, right? It's a wonderful argument to say, I cannot treat this damn thing here, this d, in terms of numbers, because there is no number to express it, the length. Right? There simply is no number. You can't express it in units. If you measure a in certain units, you can't express this d in terms of numbers, because, this is an irrational number, which means just that there are no, that's just an expression of that there is no common unit. So this was a discovery in Greek mathematics, which was, as I said, has huge consequences, long-term consequences, unbelievable, really, when you believe what happens then with the relationship between the West and the Arabic countries then, and the culture in the Middle Ages, and all that was a consequence here. The point is why I introduced that is incommensurability means, first of all, there is no common measure. Now, this term incommensurability is then transferred from mathematics here to the description of science. That is what happens in paradigm theory. The inventor of paradigm theory used this term incommensurability in order to describe the relationship between, as I said, between the old phase of normal science and the new phase of normal science. He said there is no common measure, right? And we must understand what that means, because that's a metaphor. A metaphor meaning you transfer this term from here, from mathematics, to a completely different situation, and you use the term in order to express something. And what the creator of paradigm theory wanted to express was exactly what the word says, incommensurability. There is no common measure. And now we must see what that means, right? That's not clear. You may say it's either the phase of normal science, they are incommensurable, or you may say the old and the new guiding theory are incommensurable. Is that clear so far, the mathematics stuff, and meaning no common measure, right? No common measure in which you can express both things, right? Okay. So, and the point is now, it's getting a little complicated now, but it's not in principle complicated, and simply has to be clear about these different things that are involved here. And it means a lack of a common measure, but in three different senses. Right? It's not just one sense in which normal science, old normal science and new normal science have no common measure, but they have no common measure in three different senses. And I'm going to explain to you these three different senses. And they're a little complicated, and I must give you new examples that you can understand it. Now, the first one is, and that is probably not so surprising, if you have really a new guiding framework of a new theory, then the new theory will use new concepts, different from the old theories, right? So for instance, well, I'll give you an example in a second. So we have different sets of concepts, and the point now of incommensurability is that you cannot express the new concepts in terms of the old concepts. That's the whole idea of a revolution, right? You have a somewhat radically new description of a certain area by new concepts, and if you want to understand the new concepts in terms of the old concepts, you will fail. It's just really new concepts. And you cannot express the old concepts in terms of the new concepts and vice versa. So that means we have no common measure between these concepts. They're just new concepts, and you can't express the new concepts with the old concepts. So there is no common measure in order to express these concepts, right? Now I'll give you an example, but the example unfortunately is a little difficult for you because you don't know much quantum mechanics, I guess. In quantum mechanics, you may have heard of, indeterminacy of quantum mechanics. You know that there is randomness, you never heard of it, of indeterminism of quantum mechanics at any rate. Quantum mechanics is the theory that followed Bohr's theory, and that then led to quantum mechanics. And quantum mechanics was created in 1925 and then developed until the 30s, and then it had its full form. And as I told you that in Bohr's model you have, for instance, something like the orbital of an electron. And if you look at quantum mechanics says orbitals of electrons do not exist. Doesn't exist. What does exist is a so-called wave function. That's a very abstract thing. It's a mathematical entity. Don't worry about it if you don't know what it is. It's something completely new. Quantum mechanics says there isn't an electron traveling around. That doesn't exist. Right? We have a completely new conception. What we do have is a wave. A wave, right? A wave. So if you want to have a picture of it, then you may say, so we have the center around here. There is no electron traveling around the center of the nucleus. But there is a wave around a wave, right? And the wave represents the electron. It's not the electron. It's the wave that's there. And if you, this is very hard to swallow. Of course, I know. You don't understand it. And of course, many people didn't understand it in the beginning. It's mathematics. You write it down, and you write down a function that describes this wave. And quantum mechanics says the correct description of what Bohr tried to describe by the electron traveling around the nucleus. The correct description is there is a wave around the nucleus. And that wave describes the electron, right? It's very strange. Of course it is strange, and if you don't understand it, it's wonderful, because that's exactly right? You cannot understand that in terms when you are used to thinking of an electron circling the nucleus, right? That's something you seem to understand. You say, yes, okay, I can imagine that. There's this electron, and it travels around the nucleus, wonderful, and it's a circle, or an ellipse, or whatever it is, and it travels around there, and it's stable there, yes, I get used to that, blah, 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 wonderful. And the next theory now, the next phase of normal science, people say in the new theory in quantum mechanics, sorry, there is no electron as a point, traveling around there, just doesn't exist. What is real is there is a wave, right? And the wave function is very complicated because it's a complex wave function and it's in a funny mathematical space. Don't worry about it. All I want to tell you is that the idea of a wave function, that's here, that's a very important, extremely important part of the new quantum mechanics. That idea of a wave function cannot be expressed in terms of the old concepts. It's an absolutely new concept, and you cannot understand it in terms of the old concepts. Right? That's the idea. That's the idea here, that we have a new concept in quantum mechanics, and this new concept cannot be expressed in terms of the old concepts, so we have incommensurability. We have no common measure, to express these concepts in terms of the other concepts, or these concepts in terms of the old concepts. It just doesn't work. And that's a feature of scientific revolutions, that in a scientific revolution, typically, some new concepts are introduced, and to put it somewhat loosely, and you cannot understand the new concepts in terms of the old concept. That's impossible. You cannot translate them into the old concept. That is why revolutions are so deep, because you introduce something entirely new, right? People have never dreamt of before. And you introduce something new, and the newness of, on the basis of concepts or regarding concepts is that you cannot understand the concepts, you cannot understand the new concepts in terms of the old concepts. Here's another example from electromagnetism, which is also, it's interesting, and perhaps I can just do that now for the rest of this session. And that's also something also happening in the end of the 19th century or the 20th century, and that's in electrodynamics. Now, in electrodynamics, the big discovery in the 19th century was the discovery of electromagnetic waves. We all have today electromagnetic waves. If you look at this space here, this room here, it's full of electromagnetic radiation. Not only here from the light, but also, of course, from all your handies that you have switched off, and all the television programs, and from many satellites and everything. There are thousands and thousands of thousands different electromagnetic waves in this room, right? Electromagnetic waves were discovered in the 19th century. And the fundamental idea was, when you asked the question, how is it possible that we have electromagnetic waves? How can electromagnetic waves travel through space? Which is, well, something where you say, how is that possible? The basic idea was very simple, that people said, okay, we have other phenomena of wave propagation, for instance, on water waves, right? And the water waves were quite well understood. What is a water wave? Well, you have a lake, for instance, water, and once you throw a stone in here, right, bang, then you have a wave traveling outside from the stone, right, in a circle. How does this happen? Well, it's very simple. The water is pressed here, it's pressed down here, and that water that is pressed down here is coupled with the water just next to it. So something else is pressed down here and something else is pressed down here, right? And then this one, which is pressed down here, will come back a little, right? So this one will then come back, and then this will come back, and this sort of wiggling is then a wiggling that travels outside here, right? That's the same sort of wiggling. You have a wiggling there, and because the water molecule is coupled to the next water molecule, so it gives some of its movement to the next water molecule, and this one gives it to the next water molecule, and so on and so forth. And the net result is that this wiggling in the beginning is then traveling outside, and if you have a lake, then a surface, two-dimensional, you have in water, you have these waves. If you look from above here, you throw in the stone, and these waves travel outside, right? And we have this wave traveling outside. So the basic idea here is very simple. Again, in order to have a wave that travels through space, you must have a medium, right? In that case, water. It's the water that is disturbed, and the disturbance then travels outside. That's the same with you hearing my voice. You know, why do you hear my voice? Well, we have, again, a phenomenon. It's a wave phenomenon. Here in my throat, I generate, by some wiggling. It's in that particular case, it's a vertical wiggling. In that particular case of hearing a voice, it's a longitudinal wiggling, doesn't make a difference. But the air, I'm wiggling the air, right, by talking. And the wiggling of the air propagates, because one of the air molecules are different. There are different molecules. They touch it, the next one, then the next one, and it comes to you, and in your ear it's then translated into electric impulses, and then it goes into your brain, and then you hear my voice. So the wave phenomenon, again, also in this particular case, is the phenomenon that you have a certain medium, you have a disturbance in the medium, and the disturbance travels through the medium, right? So the idea was, when electromagnetic waves were discovered, that we must have a medium, right? That we have an electric disturbance. Typically, the electric disturbance is you have a charge, right? Minus, for instance, and then you wiggle the charge, right? You play around with the charge in that way. And if you do that, then indeed you get an electromagnetic wave. So electromagnetic waves originate by moving electric charges. There we have an antenna, right? You have an antenna here, I have an antenna here, you have an antenna in your handy, and the antenna simply takes up the wave comes in, it wiggles the electrons in the antenna, and then this is translated in what you hear then in your handy. Same in television, same in satellite, and everything there. So it's always the same sort of thing. We have something wiggling, and then we have a medium, and in the medium, this wiggling then is propagated through the medium. So the idea is, of course, for electromagnetic waves, we have to have a medium, right? Something that transports the wiggling, the disturbance. So people said, yes, we need something here. It's called the electromagnetic ether. The ether in field theory. So the concept of an ether in field theory, the ether is just the medium which transports the wiggling, transports the electromagnetic field. So we need, because we have here in this, I mean, it's only air here, but air is not the medium for the electromagnetic field, it's something else, right? The air is that transports my voice to you, but it doesn't transport electromagnetic waves. They're much too fast. It can't be the ether, it can't be that. So one has to say, yes, there must be something else. That's the ether. And it's called the electromagnetic ether because it transports the electromagnetic waves. That was the situation in the 19th century. And it seems to be completely compelling that for the transportation of electromagnetic waves, there must be an ether. Right? It can't be different because an electromagnetic wave is just the traveling, the propagation of a disturbance in a medium. That's just what a wave is, right? We learn that both from water waves and from noise and voices and stuff like that. So people very firmly believed in the end of the 19th century in the existence of an electromagnetic ether with very good scientific arguments. Now the point is then what happened in the early 20th century, that one could show that there can't be any electromagnetic ether. There isn't any. Right? And people, couldn't believe it. But that was really proven. It was really shown there can't be an electromagnetic ether. But it's somehow different, namely, that absolutely empty space can transport electromagnetic waves. Empty space can transport electromagnetic waves. And if you followed my explanations here of waves, you must say that's impossible. I can't understand what you're talking about, right? That was indeed the case. You cannot understand, if you understand electromagnetic waves in terms of the ether, you cannot understand what the new physics after 1905 said, namely, no. Electromagnetic waves travel through empty space. No ether needed. Ether doesn't exist, right? This is a very strange thing, and the way the puzzlement now that you may have and say, well, that's very strange, but that's completely established. No physicist today doubts that. There is no electromagnetic ether. But electromagnetic field has the property it can travel through empty space. Yeah, you have to accept that. And now you see, that's really incommensurability. That is in terms of your earlier concept of what an electromagnetic wave is, namely the disturbance of a certain medium that propagates. In terms of this concept, it is impossible to understand the new concept. You just can't do it. But somehow you've got to get used, in the modern physics here, you have to get used to the idea, well, it's different. Electromagnetic waves travel through empty space. They do. Forget the ether. Yes? You just have to get used to this idea. And you don't get an easy picture of that, but you simply have to accept that. And that's, again, a case where you can see how strong this tension is between the old view and the new view. You cannot express the new view in terms of the old view. And that is one part of incommensurability. And that is something that has happened again and again and again in the history of science, namely that in a scientific revolution, new concepts were introduced, and the new concepts were not intelligible in terms of the old concept. And that is one of these aspects of incommensurability. Here, the incommensurability in that particular case concerning concepts, and in the next class I will show you more aspects of this incommensurability. It's quite amazing. It is something which doesn't fit your probably normal picture of how science develops, because usually you don't even hear of that incommensurability in your science education, because people don't care about this old stuff any longer. Now let me now go to the next point, and the next point may be a very surprising one for most of you, I guess, because usually what we think is that the data we are measuring are something like a fixed point in the following sense, that once you've measured certain data, then you can use them in order to compare different hypotheses. I mean, that's probably what you do, some of you at least, do in their master's thesis. You measure certain data, and the data are somehow fixed, and then you use the data, for instance, to test a hypothesis or to confirm a hypothesis, but the data is something on which you rely, right? This is the same idea, by the way, basically, that we found in inductivism, right? The fundamental idea in inductivism was, let us start with theory-free data. Theory-free means then we can rely on them. They are safe ground, right? We work from there. And that's something that I told you already in inductivism. In deductivism, it was clear that this idea had to be given up because data aren't, unfortunately, that solid, absolutely solid, that you can absolutely 100% rely on them, because the data contain theoretical elements, and the theoretical elements may be wrong. And therefore, there may be there is the possibility that you have give up or change data because of these theoretical elements. Now, in this particular case here, in paradigm theory, this element of the theory-ladenness of data, as it is sometimes called, the theory elements within the data, that leads also to some incommensurability, in the sense that you cannot use exactly the same set of data in order to evaluate different candidates now for the new theory. And that may be a little amazing, but here is the argument that the choice of data and the methods of their measurement may be influenced by the theories which make use of them. Right? This is not something completely new to you, that the theories may influence data, but here it is even, well, in a sense stronger, because I tell you more about this, not only qualitatively, that yeah, they may influence the data, fine, but it may be such that the choice of data you think that are relevant, that depends on the theories you're looking at, right? So the data are not something, again, independent of theory, but they are dependent on theory. And if you have two theories to compare with each other, then in the light of one theory you think these data are relevant, and in the light of the other theory you don't agree about the relevance of these data, okay? That sounds very funny, because we usually, probably from your training in science, as far as you got a training in science, which you all have, I guess, that we usually assume, oh, the safe side of science is the data, but that is not the case. But I give you an example to make this plausible, and the example is something you may not be familiar with, and I have to tell you first the relevant physics. The relevant physics is this, that at the end of the 19th century, or rather the last, well, in the 1860s as far as I remember, people had measured the planetary motions of the planets around the sun to a very great accuracy. And the following effect was discovered with Mercury, the most inner planet. Here you have the sun, and you have Mercury, and I'm exaggerating now. Mercury runs around the sun on an ellipse. Mercury. All right, it's an ellipse. Like the Earth around the sun, it's not a circle, it's an ellipse. But it's not that bad as this one, but that doesn't make a difference. Now the point is that Mercury, in fact, does not really run on an ellipse around the sun, but it's a more complicated thing. It's a sort of spiral. And you can describe the spiral in the following sense, that you say this ellipse itself is moving. Right? The ellipse of Mercury around the sun itself is turning, such that the real motion, now I'm exaggerating again, looks rather something like that. It goes this circle, and then it goes this circle, and then it goes this ellipse, and so on. I'm exaggerating here massively, right, in the speed. So very slowly this ellipse is turning itself. So Mercury doesn't really run the same ellipse every time, but the next time it runs a slightly displaced ellipse, and then another slightly displaced ellipse, and so on. That was discovered. And the figures here is 570, the total 570 arc minutes per 100 years. Okay? That's very little. You know, 1 minute, seconds, I'm sorry, it's seconds. So you know, 1 degree is 1/306th of the full circle. And then 1 degree has 60 minutes, right? And every minute has 60 seconds. So 1 degree is 3,600 seconds. So this is something like 1/6 of a degree, right? That's very, very little. 1/6 of a degree in 100 years, all right? So the ellipse has turned around 360 degrees in 6 times 360 is roughly, say, 2,000. And then we have wait a minute, what did I calculate just? Yeah, well, it's extremely slow. I can't calculate it in my head right now. Okay, that's the point. It's very slow, right? 1/6. So in something like 2,000 years, if I get that, no, much more, 100 years. Well, in a very long time at least, the whole thing moves around. It's a very small number. It's a very small angle, but people could measure it. Now the point is that by classical physics, by just normal classical physics, you could account for most of these 570 arc seconds. You could calculate that. For instance, the movement of Mercury is influenced by Jupiter. Jupiter is the most massive planet. Jupiter exerts gravitational effects on Mercury, and one of the effects is that the ellipse on which Mercury travels, that ellipse is moving. Also, we have the movement of the Sun. The Sun itself is rotating roughly 30 days one revolution in 30 days, and that also contributes. So the point is that people could, out of these 570 arc seconds per 100 years, they could account for most of that, right? They could calculate that from classical physics. And what was left was a small amount of 42 arc seconds that could not be accounted for. That's roughly 6% of the value. So what was the reaction of scientists at that time? That was known from the end of the 19th century. People knew that, right? They said, okay, the total effect is 570 arc seconds. We can account for almost all of it apart from 42 arc seconds. And that's, as I said, is something like 6% of that. Is that possible? Well, a little more, right? 7% of that value. So what was the reaction of the classical physicists who worked in astronomy? They said, well, we are on the right track. We can calculate 93%. There are 7% missing. We don't know why. We don't know why. There must be a mistake somewhere. There must be some additional effect we have not taken into account. Yeah, bad luck, but no catastrophe, no panic, right? Once you have an effect and you can calculate 93% of it, then you are very confident that you can calculate the rest as well, right? People said, so we can calculate, perhaps Saturn has a stronger influence, or Mars, or whatever, right? There may be many, many possible effects why this is so. People even invented an additional planet. People said it may be an additional planet in here somewhere, you know, that may account for this strange movement of Mercury. They didn't know. But nobody panicked or was insecure about classical physics. Now you see, This value then of precisely 42 arc seconds was not taken seriously, right? If it were 45 arc seconds, or if it were 40 arc seconds, or 38, was irrelevant, right? You see the point? Because it was the rest of something you could calculate, and there was some rest, a small rest, less than 10%, which you could not calculate, and the precise value of 42 seconds was just not interesting. Quite clearly, it's a rest unaccounted. You didn't know why, and whether that rest was 42 or 43 or 45 or 38 was just unimportant. You knew something was missing, you didn't know what was missing, and you said, we are certainly on the right track because we can account for 570 arc seconds, and there is some rest, and the precise value of this rest is unimportant, right? It's a datum, you measure that, said, okay, we are that far, but we don't know about the 42 arc seconds. So this is a datum, it was measured, but nobody took the exact value of 42 seconds very seriously. This would have been interesting if you have another method to calculate it, and then whether you find this difference of 42 arc seconds or you don't find it. Now the point is that changed it completely when general relativity was invented by Einstein. General relativity is a theory of gravitation that is the successor theory after Newton's theory of gravitation. And in Einstein's theory, Einstein was able to calculate exactly these 42 seconds, right? In Einstein's theory, he could exactly calculate that the missing part of that movement of Mercury was an effect coming from general relativity theory, and was, in the eyes of the general theory of relativity, a contribution to the movement of Mercury's orbit that was impossible to get from classical physics, because it was a specific effect from general relativity. So for Einstein, this particular value of 42 arc seconds was extremely important, really extremely important, because that was the exact number that Einstein could calculate with his theory, right? And that then finally convinced people because of that exact number that he could calculate. So from Einstein's point of view, the exact number of 42 arc seconds was extremely important. It was an extremely important datum. Whereas from the point of view of classical physics, it was not an important number. It was just something missing, something of the order of 7%. And people didn't care whether that was exactly 42 arc seconds or 38 or whatever. They simply knew we can't account for it, we don't know where it comes from, but it's probably no catastrophe because it's just a small part of what we can calculate, right? A small part of the whole effect that we can calculate and account for, and this small rest, we don't know where it comes from. So you see that, and if someone had said, say, someone had recalculated that stuff, and then the result would have been, say, 38 arc seconds, people would have said, okay, so 38 arc seconds. It's not important. It's a small rest. We don't know where it comes from, but the exact number does not really matter from their point of view. But from the point of view of general relativity, this number was very important, especially because general relativity could exactly account for it, right? If general relativity would have come up, say, with 38 arc seconds, they would also have said, well, this number is not very important. There's something unknown in here. But as soon as classical physics plus general relativity was able to calculate exactly these 570 arc seconds, and that the rest was accounted for by general relativity, then this number became important in the light of that theory. So you see that in a situation where you don't really know what's going on, the precise numbers sometimes are not very important because you don't know what's going on, and therefore you can't say how good this number, how important this number is, because you don't know where it arises from. And then you may say, once we understand the effect, perhaps we have to recalculate and the number will change, right? But as soon as you have a theory that tells you exactly this number, then you know it's an important number, right? It's just the prediction of your theory. And that is one of these examples where you see that slightly different sets of data are seen as relevant. Of course, both theories say, yes, altogether we have an empirical effect here, 570 arc seconds per 100 years. It's an important effect, we have to understand it. Fine, wonderful. And then you start working. And then you know that your result is not very precise. You have an error of 7%. And the exact amount of the error is not significant unless you understand exactly what the source of the error is. And then it becomes a significant number, because then it's an indicator that you have really identified the source of the error. And then you say, okay, that's marvelous, because then now we know that we really understand the phenomenon. There is a classical contribution to the phenomenon of 570 arc seconds, a classical contribution meaning to be explained by classical physics. But there is an additional contribution to these 570 arc seconds, and that is coming from general relativity. And that is because Mercury is fairly close to the Sun, and the gravitational field of the Sun is fairly strong in comparison to the other planet. And it is strong enough such that effects from general relativity can be felt. General relativity disagrees with classical Newton's gravity. The stronger the field is, the stronger the gravitational field, the stronger you feel that general relativity is the correct theory to describe what is going on. Okay, is that an example you could somehow follow, the physics as well? Right? It's a normal situation that you have in all science, that once you have something that is not accounted for, say you measure something and then you expect you have an accuracy of say 2%, then, and that means you have an error bar of 2%, then the exact value within these 2% is just unimportant. You simply know my measurement won't be more precise, and you don't want to know, usually you don't want to know what the precise reasons are why you have exactly these 2%, unless you can improve your measurement and you're interested in an improvement. Then you're interested in it, but as long as you know, okay, these 2% are good enough for what I want to do, then you're not interested in the precise causes that lead to 1.3% in one case or 0.5%. It's just unimportant. It's unimportant data. But in light of a different theory, these data may become very important. And that is one of the reasons why slightly different sets of data may be seen as relevant. And that again means incommensurability in the sense there is no common measure. In the following sense, that you don't have a fixed set of data with fixed relevance that is the same relevance for both theories. Right? That is just not the case, because it depends from which theory you look at the data. And for one theory, data may be relevant, and from another theory's point of view, they may be irrelevant. Okay, that's the second aspect of incommensurability. It's the data that have not the same relevance for both theories. And finally, there's also something a little disturbing, perhaps at first sight at least, that is that the scientific values you are using in order to evaluate the theory, in order to say which theory is better, that the scientific values you are using in the evaluation, they may depend on the theories in question, which is a very bad feedback loop, right? You want to have the values in order to evaluate theories, and then it turns out that the values are dependent on the theories. So they are not objective in a sense, They are dependent on which theory you evaluate, but that may happen. It's very unpleasant, but it may happen. And the example, this may be extremely disturbing. I mean, what's the idea of the values? Well, the idea of the values is to evaluate different candidates and then to show which one is the best one. But if the values themselves are influenced by the theories, they're not independent of the theories, right? How can they do their job? And the values, I told you, are these scientific values: the accuracy of theories, the fruitfulness, their problem-solving potential, their consistency, and so on. They are supposed, the arbiters, the referees, that say, this is a good theory, this one is a little better, and that's the very best one. right? And the referee must be independent of the things he or she is going to referee. So there is this funny situation that the values themselves are somehow influenced by the theories, and that I give you an example, and again it concerns the transition between classical physics and, in this particular case, quantum physics, which happened, as I said, in the 1920s of the last century. And the problem there is that in classical physics for something like 300 years, everyone believed that fundamental theories must be deterministic theories. Deterministic theories are theories that don't involve probabilities, right? No probability. Everything is determined, right? This is what classical physics says. Once you know the state of a universe at one particular point, you can in principle calculate it for the rest of all times. That means deterministic. It's fully determined what's going to happen in the future. So the belief from the 17th century on until the beginning of the 20th century was that a fundamental theory of physics must be deterministic. The background assumption was the universe works roughly like a clockwork, like a mechanism, right? A mechanical clock is completely deterministic. You know, you set it and then it works and works and works and works. And you can predict it precisely, right? There's no randomness or probability involved. It's just like a clockwork. And the basic idea in classical physics was the whole universe is a clockwork. If the universe is a clockwork, the fundamental theories describing the universe must be deterministic theories, right? Because the thing itself is determined in its development. So if you want to have a good theory, the theory itself must also be deterministic, namely then describing this deterministic process. So in 1925 or a little later, 1926 or 7, people realized that the new quantum mechanics that they had devised, that this new quantum mechanics was a theory that involved some indeterminism. It was not a deterministic theory. Okay? So the problem was the following. You had to make a decision between classical theories, which are deterministic, and indeterministic theories. From the experience with your deterministic theories, people had the idea that we have a value, namely the value of deterministic fundamental theories, and saying a good fundamental theory must be deterministic. If you use that value and look at quantum mechanics, you say quantum mechanics is a bad theory, right? If you come from classical physics, you say, well, that's a bad theory because it's not fully deterministic, right? But when you come from quantum mechanics, you say the basic idea of classical physics, that the universe is a deterministic mechanism, is false. It isn't, right? From this point of view, you say, no, I don't have the value that fundamental theories must be deterministic. Quantum mechanics tells us otherwise, right? So the value you are using in order to determine which one is the better fundamental theory depends on the theories. It's not independent, right? The value you have developed, that deterministic theories are highly valued in classical physics. If you apply this value, then quantum physics is out. And if you step back a little, then you realize, well, that's pure dogmatism, right? You have classical physics, you derive the value of deterministic theories, and then you value everything else in light of these values, which you have to derive from classical physics. So you're not really open for quantum mechanics, which is not a fully deterministic theory. So we have the problem here that in these revolutions, the situation may happen that the values you are used to using in evaluating theories, that they are themselves dependent on the theories, and you must give them up somehow. And the question is why? Why should you give them up, right? Why is it? Well, in this particular case, it happened that there were according to other values, the new indeterministic, partly indeterministic quantum mechanics was extremely strong, namely problem-solving capacity. It could solve problems the classical theories could not solve. And because of that value, problem-solving activities, people after a while accepted the fact that they said, well, it seems to be that determinism as a value of theories is just not as high as problem-solving activities. So people had to, evaluate their values, which is, again, an activity on another level. That they were forced to, and that was a painful process, as a matter of fact. And in the beginning, Einstein, for instance, the same Einstein from general relativity, refused to accept quantum mechanics. And he said, God does not throw dices, dices and getting numbers between 1 and 6. And quantum indeterminism is something like throwing dices. And Einstein said, no, I don't believe that. I think the universe is a deterministic system and is not some intrinsic randomness, and he couldn't accept it, right? Because he used the value that he derived from classical physics, and he was convinced that these are the right values. So the situation may become very tricky, as it did in the 20th century in that particular case, that the values you are using are not really completely unbiased, but they are also influenced by the theories themselves, right? Like the data. The relevance of the data depends on the theory from whose viewpoint you look at the data. And the same is here. The values themselves are somehow, or can be somehow, dependent on the theories, and then they lose their complete neutrality. And then you have to play around with the values, and that means you are lacking a common measure how to evaluate the theories. Namely, that would be a fixed set of values from which you look at the theories and then evaluate them. Same with the data, you are lacking a fixed set of data which are then relevant for the evaluation of the theories. So what is happening here in these scientific revolutions is somehow that you're losing your absolute neutral yardsticks by which to evaluate the theories. And that is exactly incommensurability. And that makes, therefore, the evaluation of competing theories during a scientific revolution more difficult than one usually imagines, because usually one thinks, well, there are data, and when we evaluate the theories with the data, we know what a good theory is. And then we evaluate the theories according to these values. We have a common measure, namely values and data, right? And incommensurability says, no, if you look close enough, that's just not true. Because a revolution is something, a scientific revolution, may be something so deep that it even affects the data, and it even affects the value you are commonly using to evaluate theories. And that makes scientific development much more complicated than was thought before, and this is one of the great, I think, virtues and achievements of paradigm theory, namely making people aware how complicated these processes are that happen in especially scientific revolutions.
Professor?
Yeah.
I don't seem to get this point. Are you saying that even before you start the application of this data set to the theory, to test the hypothesis, in a way they are theory-leading? It's my...
Well, just take the examples. I mean, it's just that, as I said, take which one? You have difficulties with the data, that the data...
Yeah, the data is before you start the application of that data to the hypothesis.
Yeah.
They are already influenced.
They are influenced, yes. Yeah. For instance, I mean, you measure, if you take especially these 42 arc seconds, the 42 per century, this is not directly measured, right? These 42 arc seconds that are relevant then for general relativity are not directly measured. What is directly measured is the 470 arc seconds. That is something you can measure, right? And then you start using theories, namely Newtonian gravitational theory. And then you calculate, then you start calculating. You calculate the influence of the sun. There's also a geometrical effect coming from Earth movement. the influence of the Sun, the influence of Jupiter, and this geometrical effect. You use the theory.
No, I mean before you start using the theory itself.
Before you start using the theory, you have to measure these 570 arc seconds. That's a measured thing. Of course, you need a theory of your measuring instruments. This is also not, you don't look there and see, oh, 570 arc seconds per century. It's a very complicated measurement, of course, in which many theories are already involved in the measuring processes, right? You must evaluate your telescopes, you must evaluate your instruments to measure a certain angle, and so on and so forth, right? You have time measurement, a very complicated time measurement, but this one is a fairly, well, comparatively directly measured number, 570 arc seconds per century, right? That is measured, right? Other theories do play a role here. But the next step is when you account for that, when you say, why is it that Mercury moves, the Mercury's ellipse moves in this way? Then you start calculating by means of theory, right? You say, what's the influence of Jupiter? Jupiter sits down here somewhat, has a gravitational field, influences that, and then you get a certain amount by Jupiter, all right? You say, okay, say 50%, I don't know the numbers here. And then you say, okay, the Sun is rotating, and that changes something. And then you calculate only on the basis of the theory, right? Of course, you have to measure the mass of Jupiter. You can't measure directly the mass of Jupiter, but you use Newtonian theory again. You calculate the mass of Jupiter by the frequency, by the diameter of the orbit, and the frequency, then you can calculate the mass, right? It's not directly measured. You use Newtonian theory already. So anyway, so you calculate, then you only calculate, right? The influence of Jupiter, the influence of the Sun, the rotation of the Sun, and this geometrical influence. That's calculated. And then you get a rest, and the rest is 42 seconds. This is not directly measured, but it's derived from this value plus lots of theory, and then you have this number. And what you believe is this is a number that is not accounted for, right? It's part of this movement. So in a sense, it's of course a measured number, but a measured number that has a lot of theory inbuilt. It's not directly measured such that you take a telescope, look out there, look for 5 seconds, and then you have measured 42 arc seconds. No way. It's a very complicated thing, but still you think this is something in principle measured, right? This is a datum, right? And now the point is, how seriously do you take the exact number here of 42? How seriously do you take it? Well, you know, when you come from Newtonian physics, you know that something is not right, right? 7%. And you don't know where it comes from. You have no idea where it comes from. So you don't even know whether this number is correctly calculated. You don't know that. Because, as I said, that's the rest once you have calculated Jupiter's influence, the Sun influence, and the geometry, right? And you know something is wrong, but you don't know where something is wrong. So you don't even trust this number very strongly. You simply know, look, I don't get, in the end, these 570 arc seconds. But you don't know where the mistake is, you know, where the error is, what went wrong. You don't know that. And therefore, you don't trust this particular number, not very specifically. Because you simply know, look, my calculations are good to roughly 7%. And you don't know more. And once you simply know, well, my mistake is something, my error is something like 7%, you don't even know whether it's only 3%. You just know this is unaccounted for, and you don't know the source, right? This is unaccounted for. And once you don't know the source, you must also, you say, well, do I have Jupiter's influence really right? I don't know. Do I have the Sun's influence really right? Is there something missing that I haven't accounted at all? I don't know, right? This, just the fact that this is different, that this is the rest here, tells you that you are not in command, in full command of the situation, that something is wrong, right? You don't know what is wrong. And therefore you don't trust this number really very strongly. You can't. You don't know. You simply say, look, I know something is wrong, and what I so far see is that the difference is 42 arc seconds. But that's certainly not a number you wouldn't trust very strongly, because you simply know something is wrong, right? And because it's wrong, you can't trust what you calculated fully. You just say something is missing and I don't know what is missing. But the point is completely different when you now start from a completely different theory, namely from general relativity. And general relativity, without taking into account the rest of it, but really purely theoretically, calculates you that the number, the missing, or what is this, the effect deriving from general relativity in contrast to Newtonian physics, that this is exactly 42 seconds. That's a precise prediction of the theory itself. And then you say, look, this is exactly what my theory, my general relativity says, and then this number becomes extremely relevant. Because just imagine it would have been 38 arc seconds here, or say 59, and general relativity calculates 42, then people would say, so, what to do with it? It could be general relativity, but perhaps something else. Perhaps general relativity is not right. People didn't know whether general relativity was the right theory, right, at that particular point. That was calculated in 1916. General relativity was invented in 1915, and people didn't know. I mean, it was a theory, you know, a successor for Newton's gravitation, but people didn't know whether it's the right theory. So they didn't know. So just imagine it would have been, this value would have been different, say 37, and general relativity calculates 42. People would have said, yeah, that could be a coincidence. Pure luck, right? It's not the right number. Perhaps, yeah. Who knows, right? And nobody would, and the situation would still have been open, right? Because nobody can trust this exact figure unless you know what's going on. But as soon as you know that general relativity, who could do other things as well, can calculate exactly this missing value, then you think, now we do understand the situation fully, right? And then the number becomes extremely important, right? It's a complicated story. It's good that you asked me again, because it's really a question, as you see, of judgment, right? You have this number, and then the question is, shall I trust this number? Right? That's the question. And there's no pure methodology how you can say, yes, it's clear that you can trust it, or that it's clear that you can't trust it. It's a question of judgment. You have a difficult situation. You know, you have this situation, 570 arc seconds. You can calculate most of it, 93%, which gives you the confidence, should be okay in principle. Something is missing. You know that from hundreds of years that you can never calculate fully precisely, or almost never. And there's always something missing because you have approximations and the measurements are not precise and whatnot, right? You know that. And 7% is such that people said, yeah, we don't know, but, you know, we are on the right track. We can calculate 93% of the effect. Damn it, we should get the last 7% as well when we refine the measurement or refine the calculation or do a little trickling and wiggling, and then we'll get it in the end. So people weren't really in panic. They said, yeah, 7% is missing. That's a nuisance. Of course, it would be better to have only 1% missing, but we have 7%. Yeah, bad luck, damn it. But it's no sign that something is fundamentally wrong. Right? It's just no sign. If classical physics would have said, say, if classical had said, there is impossible that this ellipse moves in a circle. It's impossible. It must be fixed according to classical physics. Then people would have said, of course, there must be something wrong with classical physics because it's really moving. 570 arc seconds per 100 years. It's very, very little, but it's moving. And if classical physics is absolutely unable to account for that, then the theory must be wrong. There must be something deeply wrong, right? But that wasn't the case. It was able 93% of the effect to explain. Look, these are very, very small things, right? This is, as I said, it's the sixth of an arc in 100 years. Now, let's say a sixth of an arc, so it's in 600 years. It's one degree in 600 years times 360 times 6, so it's something like 2,000 years, right? It moves around in, is it 2,000 or 20,000? I don't know, 20,000 rather. So in 20,000 years, the ellipse moves once around full circle. In 20,000 years, it's a very long time. You measure perhaps in 2 years or something, you measure that, and then you come up with this number, right? So it's very small numbers, and it's very delicate. It's very delicate measurements, it's very delicate calculations, because this is perturbation theory that you have to use to influence. Look, it's not only Jupiter, there's also Saturn and the other planets, and their influence is much smaller, so people usually said it's Jupiter mainly because it's most massive, and the Sun, of course, because it's so close. And who knows what's going on there? Perhaps there is some gas in between Mercury and the Sun that has some effect, you know? We don't know. People didn't know so much. So there are so many different sources that you couldn't really trust this figure, that you couldn't. And therefore people said, yeah, it's something not so important, but the number becomes extremely important, this precise number, once general relativity predicts it, right? Then you say, wow, that's significant. That's not an accident, right? That exactly this number is predicted. And then the number becomes extremely important. Okay, does this clarify the confusion, right? This is, you're absolutely correct with your question, because it is a little complicated, and especially since you do not know so much about the physics, but it's very important, I think, to understand that, because this is much more sophisticated and complicated than the normal stories you hear about science, right? The normal standard stories, yeah, you measure something and test the hypothesis and blah, blah, blah. You know, real science is much more complicated. And incommensurability is one of these aspects that has been a topic for discussion for the last 50 years, because it's fairly complicated. You have to fairly well understand particular situations like this one in order to grasp what's going on here with incommensurability. And the point is, that explains then, as I'm going to tell you after the break, perhaps I should say that right now, yes, that incommensurability does not make theory comparison impossible. I mean, although you don't have this fixed yardstick how to measure, namely data or values or something, you don't have them, but it makes it much more difficult than it is commonly assumed. Usually people think in the more simplified pictures of science that you know, in principle, doing this theory comparison, you just look which theory is better with regard to the data, and here you go, and the one that's better with respect to the data will win. It's much more complicated. That is what I'm saying here, that incommensurability presents difficulties to theory comparison, but it does not make theory comparison impossible. As we have seen in the history of science, people made up their mind, and they found arguments why they thought this theory is really the best one, and this is the one by which we now proceed. And for instance, in the case of general relativity, from 1915 on, this has been the general framework for physics, and I'll come back to general relativity in a few minutes. Okay, so this may be for you, that this may be a little surprising why I say that it's not impossible, but the point is that many people who read paradigm theory, they believed that the author of paradigm theory wanted to say that a rational theory comparison was just impossible. And he never wanted to say that. He just said, look, if you look at the history of science, then you find the phenomenon of incommensurability, and incommensurability just makes theory comparison much more delicate, right? Complicated. And you need judgment, as I tried to show you with that example, that you really need judgment. It's a tricky thing. It's not straightforward. You have to think about it and make a judgment. And it doesn't make a theory comparison impossible, as some commentators, quite a few commentators in the beginning believed, because they didn't understand the theory well enough. Okay. So therefore, if you say, well, that's trivial, so forget it, fine, it's just something that you may find in the literature. Okay, so one of these effects is here, that theory comparison is so difficult, it helps explain why theory choice in the sciences is sometimes a quite lengthy process. It takes a long time. If you look at the Copernican revolution, the revolution, you know, from the, I talked about it, from the geocentric to the heliocentric point of view, you know, the sun in the center of the earth in the center of the world and the sun in the center of the world, that was a process that took roughly 150 years. 150 years. Because you had this sort of incommensurability stuff and it was difficult to evaluate. And also, I told you that the question of the acceptance of Bohr's model, the atomic model, which seems so smashingly successful, it also took 2 years. People couldn't couldn't make up their mind whether the whole game that Bohr proposed, calculating properties of atoms, was just, playing around with numbers with no physical significance. People didn't believe it. They said, that's very funny, it's inconsistent and it somehow works, but shall we take it seriously? It's not clear. So that explains why theory choice in science is sometimes a lengthy process, which you cannot understand if you have simply data, fixed data, and you evaluate the theories according to the data, because the decision is quick. Like most decisions, I'm told, in experimental chemistry, are fairly quick. If you have a doubt something, you set up an experiment, and you make the experiment, you run the experiment, and the disagreement is dissolved, because you can simply decide it on the basis of experiments in experimental chemistry in many cases. But when it comes to the larger theories like quantum mechanics, gravitation, and so on and so forth, the situation becomes more complicated. Okay. Now, the thing that is perhaps interesting for you is that incommensurability does not only apply to the relationship between normal science traditions or fundamental science, but also to the relationships between the schools of pre-normal science. Okay, so don't worry about it, schools about normal science. Here's the point that may be of interest to you, but in somewhat modified form, it concerns also the relationships between different cultures. And that's, of course, because you come basically from other cultures than the Western cultures. Your home culture, at least of most of you, is different from the one that you find here in the West, although your home countries, most of them moving towards the West to some degree. But if you look, say, to your grandparents, and one of the very interesting examples is healing, is medicine, healing procedures. If you imagine what your grandparents think about efficient way of healings, as long as they are not influenced by the Western medical tradition, but the traditions that are in your home country, whichever it is, right? If you come from Africa, for instance, or Asia, then you have traditions there of healing which are very different from the Western traditions. And if you want to talk to your grandmother and explain to her why you believe in the Western tradition of healing and what the arguments are, if you do, I don't know whether you do, but if you want to compare the Western tradition of medicine and of healing, and then you ask your grandmother if she's a traditional woman, and when she talks about healing, what is relevant to her, and what to her are relevant data, even if she comes from a tradition that's very, very alien to the Western tradition, she usually has arguments. She just doesn't say, yes, I do that, period. But she can present arguments from the other tradition. But if you want to evaluate the arguments from that tradition in terms of the Western tradition, you don't understand a word, right? It's when it comes, say, to voodoo. You can't understand voodoo in Western terms at all, right? In the same way as you can't understand from the point of view of voodoo. I'm not telling you buy voodoo, it's the best to do. I'm not saying that. I'm simply saying if you compare these traditions, if you try to understand from the voodoo point of view, say some things that happen in your life which are unexplainable, and then you say, well, voodoo gives me a framework how to explain that. If you want to understand what Western medicine does in terms of voodoo, there is no way. You can't reproduce what Western medicine does in terms of voodoo. It's incommensurable. In the same way, you can't explain and describe what voodoo does in terms of Western medicine. You can't translate these frameworks. It's just impossible. And voodoo is a more extreme example. You can also have, say, things of herbal healing, where Western medicine says perhaps, well, we don't understand, we don't know what the content of these herbs are, why are they healing, we don't believe it, why is it important to have these circumstances, which may be part of a tradition. So the point is that I'm trying to make, it's not that the importance is not these particular examples, whether it's voodoo or not, you may like or dislike it, that's not my point. My point is when it comes to a relationship between different cultures, right? Say the Western scientific culture and cultures in your home country, whether it concerns healing or other things, relationships, description of relationships, and so on. The point is that the difficulties in making contact between these different cultures, that is usually a case of incommensurability. You do not have a common measure. You know, you don't have a fixed point that's valid in both cultures, right? Such that you can say, okay, I can compare them with respect to this common measure. It simply doesn't exist. And that explains, once you work that out in more detail, whatever the particular situation is, that explains why it is so difficult to make contact between different cultures. And I guess for some of you, it's a rather painful process to adapt here to some degree to the Western culture, because it's something where you have other parts from your own home culture which you cannot translate in here, and you cannot really evaluate from the point of view of Western culture. On the other hand, there are things in Western culture that may be alien to you somehow. You say, well, it's a successful science, therefore, and I'm a scientist, so it's better that I stick to them. But you can't really, you know, make a solid bridge between the parts of yourself, right? And that is because of incommensurability. There is no common measure. The concepts are fundamentally different between different cultures. The ideas what is relevant data is really different. If you talk to someone why he thinks here is a case from which you see there is a voodoo influence, he comes or she may come with data which you say, come on, they're completely irrelevant. And the other person will say, no, you're wrong. They are relevant. You know, they show this is the influence of that and that practice of that person, right? You say, no, they're absolutely irrelevant data. You have the same effect here with the data. You cannot translate the concepts, and also the values by which you evaluate are very different. You know, when you evaluate a certain tradition and then you think that from a certain local tradition, indigenous tradition, they have values to show what is important and what is unimportant, that's very different from what is, from the point of view of the Western culture and Western science, what is important and what is unimportant. So you're lacking a common basis of values in order to evaluate. And therefore, I think this topic of incommensurability, it's much more relevant and important than just for the explanation of the history of science and for paradigm theory. I think it's something that's very important in our globalizing world, of which you are a part. You know, you are really an indicator for globalization. You come to this country in order to learn Western science and Western engineering, and you have then to deal with what you bring with you from your home country to this Western culture, and then we have this clash of cultures, and it's happening inside you, and of course inside also your families, when you come home and tell them what the Western world is like, as far as they don't know about it by television and so on and so forth.